Hello, everyone, and we are going to be talking about the advancement in microvibration management for spacecraft flywheel rotor systems. Um, this essentially is the system that allows satellites to stay in proper position, allows them to not just be spinning out of control, and allows them to point where we need them to point. Um, the importance of high precision, specifically flywheels, is to obtain high quality remote sensing imaging. For example, if we have weather satellites which are on geosynchronous orbit, the satellite sometimes needs to point at a very precise location in the air to be able to analyze um, certain weather patterns or clouds or things like that. We need to be able to accurately calculate where the sensors are looking at. Otherwise, we're just be getting a bunch of useless information. Um, this is most notably important in deep space physical exploration, where we analyze other bodies in space, such as like how Hubble takes pictures of other like stars or galaxies or other astronomical bodies. Um, we actually also have satellite laser communications. The most recent example that I know of, for example, was the of Voyager, which is so far in deep space outside of the solar system by now, I believe, um, that the antenna is having a lot of problems still pointing towards Earth. Because by now it's literally like if the most minimal like changing direction of the satellite happens, then the satellite will literally be just pointing somewhere extremely different. And this is a very important thing for engineers to understand, so that the satellite has an optimal lifetime and no issues happen with regarding this. Um, what are spacecraft flywheel rotor systems specifically? Essentially, it's sort of like a heavy wheel that is spinning really fast. Some of these speeds can go anywhere from 4,000 to 9,000 revolutions per minute. Um, they allow the satellite to be stable. If you've ever seen videos of what happens when you spin a wheel, and all of a sudden you kind of like hold it on the side, the wheel will like stand vertically aligned because of the conservation of momentum, of angular momentum. Um, this specifically is the main source of microvibrations in satellites, and like we said before, this is very important to have in mind, because if we have a high precision satellite like Hubble, or right now like the James Webb Space Telescope, the satellite would basically be useless if we don't have into account these microvibrations, um, which will, if unaccounted for, they will ruin all the data being and coming from the satellite. Some of the main sources and impacts of microvibrations, we have a mechanical source, electromagnetic, structural disturbance, and structural disturbances. Um, for the mechanical disturbances, we have rotor unbalances. So if the rotors are not properly aligned, irrational characteristics of rolling bearings. Again, if the bearings are not within a certain tolerance of precision. We have the flywheel rotor rub impact. So if it's not completely precise, or if the rotor unaligns itself while it's rotating, it will cause a lot of micro vibrations. We have electromagnetic disturbances. We have torque ripple of the driving motor and imbalance of magnetic pole force. Sometimes these flywheels will be magnetically aligned, and errors within that spectrum would cause the controls in the satellite to believe that it's actually somewhere it is not, and it will cause problems. And then structural disturbances, the flywheel vibrations, like I said, improper alignment, flexibility of the stroke support and clearance effect. All of these can be causes of microvibrations and high impacts on your satellites. How can we fix this? The paper that I'm specifically reading at talks specifically about how we can properly fix this. They talk about different methods. The one that I thought was the easiest, just because it doesn't have that many extra components, is the damping of the structure. Essentially, this is what a usual flywheel looks like. What they were trying to argue about was that applying bearing assemblies and elastic supports would allow for the dampening of the structure and prevent the imperfections of the wheel to affect the entirety of the satellite, or at least to mitigate it a lot. This is kind of like springs that we learned from in class. We also have vibration isolators, magnetic bearings, and active control systems. Again, I believe the best one here is damping structures, just because it requires a lot less moving parts, and it's the most natural one. Active control systems are really good, but it also implements another degree of failure or more complexity to the system, and that does not usually mean that the system will be better. Some of the challenges that we see for the future are because we are coming to an age where we're starting to explore a lot more deep space objects, such as Mars, Jupiter, the moons of Saturn. We also have some telescopes in deep space. The James Webb Space Telescope is in Lagrange point, which, also it's kind of far. And James Webb is like imaging objects millions of light years away, and the precision in this type of telescopes cannot be underestimated. Another problem is the system complexity. Like I said before, putting an active control system would increase the system complexity, and any movable parts also increases the system complexity, and that could help. But if you're not careful and make sure that all the tolerances are proper, then it could easily ruin your program. Cost, obviously, when we launch satellites, there's a cost that we have to account for. We cannot just throw money at an issue and be like, okay, it's fine. We just, out of the $10 million budget we have for the satellite, we just tossed $5 million into vibration systems, and we only have $5 million to do the entirety of the other part of the satellite. And we also have performance. So again, make sure that every piece on your satellite works, essentially. Thanks for watching. This research paper was actually very interesting. I learned a lot of things that I did not know before. I am going to be leaving the research paper in the description. And thank you so much for watching.